Welcome. In today's video, we're going to be looking at how mathematical induction can be used to deal with proofs of divisibility. But before we do that, I'm going to take a look at some notation that can help us simplify or at least shorten the length of our proofs. So what do we mean actually by divisibility? Well, we say that the number b is divisible by the number a if when you take b and you divide it by a, you have a result m, and that this m is an element of the natural numbers. Equivalently, we could also write that b is equal to m times a, where m is an element of the natural numbers. Again, that's just by rearranging this fraction up here above. We could equally say that a is a multiple, or b is a multiple of a. So what we would write in this case is a with this funny looking stick symbol means that a divides b, or in other words that a goes into b a multiple of m times, or a or b is divisible by a. And in fact, we would write a funny looking stick symbol with a line through it to say that a does not divide b. So for example, if we have a look at this 8 divided by 2, so 8 divided by 2 is equal to 4, which means 2 goes into 8 quite nicely, and so we would write 2 divides 8. But, and 4 of course is an element of the natural numbers. That's how we know 2 divides 8, but of course the opposite is if we were to write something like 9 divided by 2. 9 divided by 2 is equal to 4.5, which is not an element of the natural numbers. It doesn't nicely go, 2 does not go nicely into 9, and so what we would write is 2 does not divide 9. So now that we're familiar with this notation, we're going to extend it a little bit and take a look at some proofs involving divisibility and induction. So let's have a look at the first example. Using mathematical induction, prove that 3 goes into n cubed minus n for all values of n that are an element of the natural numbers. Well, again, these induction proofs will consist of 2 basic steps. Step 1, the basis case, and step 2, the inductive step. So again, we're going to start with the initial step, or the basis case. So, well, firstly, actually, what we're going to do is define the proposition Pn. So Pn is the proposition that 3 goes into n cubed minus n for all n an element of the natural numbers. That is, of course, defining the proposition. Now we can do the basis case. So the basis case is, let's have a look at for n equals 1. So for n equals 1, what we have is that n cubed minus n is 1 cubed minus 1, which equals 0. And so P of n is true for n equals 1. Now why is P of n true? Well, 3 technically divides 0. 3 goes into 0 0 times, and therefore we say 3 divides 0. So we have shown, at least for the case where n equals 1, that P of n is true. Now let's have a look at the inductive step. Assume Pn is true for some n equals k, where k is greater than or equal to 1. In other words, or that is, we're going to assume 3k, or 3 goes into k cubed minus k. Now, equivalently, what we could write here, instead of saying this notation is a little bit difficult. What does it even mean? 3 goes into this. However, what we are going to write, we're going to kind of shift this problem into sort of an equality problem by saying, well, if 3 goes into k cubed minus k, then what we can say is that k cubed minus k is equal to 3 times some number m, where m is an element of the natural numbers. That's what it means to be divisible. If 3 goes into k cubed minus k, then we can equally write k cubed minus k is equal to 3m. And that's what we saw actually in the previous or 2 slides ago when we were defining divisibility. So now what we can do is we can do the inductive step. So for the inductive step, again, we look at when n is equal to k plus 1. And so when n equals k plus 1, what do we have? Well, the left, or the n cubed minus n, what does that look like? That looks like k plus 1 cubed minus k plus 1. Now, I want us to remember again, how do we do these inductive steps? What we want to do is we want to make the k plus 1 case, this is the k plus 1 case, look similar to the k case. So if we have a look here, we kind of want to extract k cubed minus k, this is the k case. We want to try and make our k plus 1 case look similar to that. So the first thing I'm going to do is I'm going to expand the brackets here. And I expand the brackets here because I'm going to get a k cubed when I expand these brackets. And I'm also going to have a minus k. And that actually mirrors the k case. So let's do that now. So here you'll notice what I've written is I've written k cubed plus 3k squared plus 3k plus 1. This is the expanded version of that cubic there. That's using the binomial theorem. This, of course, would be 3 choose 1. This would be 3 choose 2. This would be 3 choose 3. And this would be 3 choose 0. And, of course, we still have the minus k and the minus 1 here at the front. Now, the plus 1 and the minus 1 will cancel with each other. And now you'll notice that, again, what I said before, we've got the k cubed minus k here. Again, that's going to look like our k case. So that's what I've rewritten in the next step. I've got my k cubed minus k. And I've got my 3k squared plus 3k here. Now, this is the step that matters the most in the divisibility proofs. Remember, on the previous slide, I said that k cubed minus k could be written as 3m. So that's what I'm going to do. I'm going to write that as 3m. K cubed minus k, rewrite that as 3m. Equally, what I notice here is I could take a common factor out of 3 out of this, this sum here, 3k squared plus 3k, to form 3k squared plus k in brackets. And now we can actually take the 3 out as a common factor of the whole expression to have something that looks like 3m plus k squared plus k. And what do you know? What have we actually proven here? Well, we've proven 3 definitely goes into 3 times something. Because you know m is an element of the natural numbers, k squared is an element of the natural numbers, k is an element of the natural numbers. So altogether, this particular expression here is a whole number, m plus k squared plus k, which means if their summation is a whole number, then multiplying their summation by 3 will give me a number that is that is divisible by 3. And that's what I've written here. 3 definitely goes into 3 times some whole number. And so then we can say, well, 3 goes into this expression. And so it follows that if P of n is true, remember P of n is true for n equals k. Remember that was shown by the assumption k cubed minus k is equal to 3m. Because it's true for n equals k, then it is also true for n is equal to k plus 1. And since P of n is true for n equals 1, and P of n is true for n equals k implies P of n is true for n is equal to k plus 1, we have shown by the principle of mathematical induction P of n is true for all values of n, an element in the natural numbers. Let's take a look at another example to cement this idea of divisibility and how we deal with these divisibility proofs. Using mathematical induction, prove that 4 goes into 7 to the power of n minus 3 to the power of n for all n an element of the natural numbers. So again, what we first do is define P of n is the proposition that 4 goes into 7 to the power of n minus 3 to the power of n for all n an element in the natural numbers. And then we're going to try our initial step or our initial case. So for n equals 1, that is the first term in the natural numbers. For n equals 1, what we have is 7 to the power of n minus 3 to the power of n is equal to 7 to the power of 1 minus 3 to the power of 1, which equals 4. And 4 definitely goes into 4. And so Pn is true for n equals 1. Now we begin the inductive step. And so again, what we're going to do is we're going to assume Pn is true for some n equals k, where k is greater than or equal to 1. In other words, we're going to assume 4 goes into 7 to the power of k minus 3 to the power of k. And now what we can rewrite this, remember we can rewrite this divisibility statement as sort of an equality statement involving now, we can write 7k minus 3k can be represented as 4m, where m is an element of the natural numbers. And now we're going to look at the case where n equals k plus 1. So when we do have n equals k plus 1, we've got 7 to the power of n minus 3 to the power of n. Replace our n's with k plus 1 and k plus 1 here. Now, here is where our assumption needs to be kind of forced, not forced, but caressed, let's say, into our equation. Again, if we look at the previous statement, what we want to see here is this 7 to the k minus 3 to the k. So what I'm going to do from this step here, see how we have 7 to the k plus 1 and 3 to the k plus 1? I'm going to first rewrite that as 7 times 7 to the k minus 3 times 3 to the k. And I've done that because now I've got this 7 to the k and I've got this 3 to the k. What can I write now? Well, I can actually rewrite this 7 to the k here as, 7 times 7 to the k as 4 times 7 to the k plus 3 times 7 to the k. Now there's a reason why I've kind of done that. And the reason here, the first reason I've split that is because, well, I've got 4 times something, so I know at least this part of the expression will be divisible by 4. But also you see how I've got a minus 3 times 3 to the k, and now I've got a plus 3 times 7 to the k, which means I might be able to take a common factor out of 3 here. And as you'll see in the next step, that's exactly what I've done. I've taken a common factor of 3 between these two expressions here. And now you'll notice I've actually nicely forced in our assumption. Here is our assumption step. Here is the 7k minus 3k. And actually, in the next step, what we can replace this 7k minus 3k, we can replace it with 4m. And now you've got 4 times some number here and 4 times some number here. And again, we can take out the 4 as a common factor. And we know that this expression inside the brackets is definitely a natural number or a whole number. So 4 times this whole number here is going to give me a number divisible by 4. So again, it was a bit of forcing into the equation what we wanted. Again, here in that first step, we tried to get our 7 to the k and our 3 to the k. In this next step, I split that 7 times 7 to the k in a strategic way, knowing that I'd be able to factor out our assumption in this step here, and knowing that this part of the 7 to the k would be divisible by 4, or 4 times 7 to the k is divisible by 4, and this part of the assumption would also be divisible by 4. And so we can now write again, because it's rewritten or written as 4 times some number, we've definitely got that 4 goes into 4 times some number, and then because therefore we've shown that if P of n is true for n equals k, that was our assumption of 4m, this implies Pn is also true for n is equal to k plus 1. And since P of n is true for n equals 1, and P of n is true for n equals k, implies that P of n is also true for n equals k plus 1, we can write by the principle of mathematical induction, Pn is true for all n is an element of the natural numbers. And that concludes our series on mathematical induction.